shortly. I'll wait until, okay, it's told me it's gone live on YouTube. It's just the easiest way for me to record stuff. Otherwise I have to record it to my local drive and then upload it after the fact, and I nearly always forget to upload it. At least the live stream is pretty good. It drops frames sometimes, so maybe the video pauses a bit, but it's usually pretty good with the full screen, and the audio's okay. Okay, so that's where we are. Last week we talked about mesh analysis, and I need to we need to do some stuff about that. I think if everybody can mute. I'm getting a bit of feedback through Franklin. Can you? Yeah, thank you. So that's where we are. One thing I need to do for next week, you'll notice here is where I was planning to do midterm 1. So what I try to do is give you 2 weeks notice about what's on the midterm. So next week I will talk about what's on the midterm paper, and I realize this is a little dumb, but I give you the paper 2 weeks before the exam, and the aim is that then you when you come to the exam, and you'll have to book your times because it's a Zoom or a Discord session, I'll give you and you'll basically talk me through how you solve the problems that I'm going to ask you. And I think last week or the week before I gave you some examples, but next week I'll release this semester's paper, the first paper, and the topic is, and Mehul Kumar, I think I'm getting some feedback through yours. Thank you. Yeah, the and yeah, you'll have to answer some questions online. The topics, that's right. It's going to be the first piece that we did, the basic concepts, resistance from shape, resistance change with temperature, and converting between charge in electrons and time and current and that sort of thing. Okay, those 3 topics that we looked at in the first tutorial sheet. But I'll release that next week, and we'll go through it. So we've actually covered a lot of the stuff. Unfortunately, the stuff we haven't covered, it's going to take a little longer to get through. The earlier stuff is sort of foundational, and we need to go through it. And the later stuff, as you saw with mesh analysis last week, is a bit more algorithmic, so there's a bit more to it, and we need to move through some of those things. It's okay. You've got a freebie this week. There's nothing due today. I decided to do that because I was late in releasing the homework and getting the labs organized. Having said that, you will notice that I think all but one of the labs is now available, and maybe all but one of the homework assignments is now available. Okay. That reminds me, I need to show you what I'm asking you to do for the homework assignments from now on is to go to WebWork, right? Professor Broderick has set that up. WebWork lets me put together more complicated questions and answers than Blackboard does. So what you're going to have to do is log in to WebWork, and the instructions for figuring out what your username and password are down here, right? So if your name is Abel Baker-Charlie, then your username is your first initial and then your last name or your family name run together. Okay, and it's all in lowercase. And then your password, if your name is Abel Baker Charlie and your student number is 012345667, then the first 4 letters of your family name and the last 4 digits of your student ID should be your password. If it's not, let me know and I'll fix it. But I believe everything's set up correctly to do that. Let's just go to the website. Okay. Professor Broderick had some other ones for the other sorts of questions we've looked at, the fundamental stuff and the KVL, Kirchhoff's voltage law, Kirchhoff's current law, and voltage and current dividers. But we've already covered those in homeworks 1 through 3 in Blackboard, so I'm not going to be using those. But these are the others. The currently open one that is due on March 6th is the mesh analysis one, and there's 5 problems. You can attempt things on WebWork as often as it takes to get them right. Okay, and sometimes the what WebWork is asking for might not be as obvious as it could be. So please persevere, and if after a couple of tries it doesn't work, ask a question either during class or bounce me an email. My email response tends to be a bit erratic on Tuesdays and Fridays. I am very busy teaching, so I don't have time to respond much on Tuesdays and Fridays, but other times I do. Sending me a chat in Discord might be the quickest, depends on what I need to do to get you an answer. That's also an option. And again, my response time varies wildly. Sometimes I'll respond within a minute, and other times it'll take me a day. So just be a bit patient. So here's the first mesh analysis problem, and there's 4 parts to the problem. First part is, what type of equations do we need? And in this particular example, we only need Kirchhoff voltage law equations. And I'll talk a bit more about what others. So if you remember, towards the end of last week's talk, we talked about super meshes. And when there's a super mesh requirement to analyze the circuit, then you've got to use a Kcl equation rather than and a KVL, but one of the Kvl equations that you would normally think about turns into a Kirchhoff's current law equation. But I'll talk through that. And then the system of equations, it gives you some values for the voltage and values for the resistors in the circuit. And then you've basically got to try and figure out what the equations are, right? The KVL for I1, go around the circuit. V1 is 14, and we're going into the negative side, so it's minus 14, and then plus, that's I1 minus I3, right? In fact, let's just take that image, and I'll talk to that. The things you have to, it doesn't really matter what order things go in these equations. What matters is that the only variables, the only non-numeric things that are allowed to go in there that give a valid answer are the I1, I2 and I3. For example, you can't put V1 in there. You can't put R1 in there and expect the answer to be correct. Okay. But try it. You can try submitting answers as often as you like. And the nice thing about this is, the thing that people usually forget in these sorts of questions is the question is actually asking what is V out, right? And people often solve the equation perfectly correctly, excuse me, and then forget to if we're doing this on paper, people forget to answer what V out is. But this form of, right, it explicitly asks you, and it will tell you you've got it wrong if you don't finish it off. And there's some numbers. I think these values are randomly generated for everybody, so showing you this is not going to show you the solution. Anyway, so what I want you to do, once you've made your attempt at excuse me, at your homework in WebWork, I need you to go back to Blackboard and just tell me that you've done it. If you want to, you can attach a screenshot of your WebWork result. That'll help me. But all you really need to do is say done and submit. Okay. And because this is me, I'm not actually a student, so I'm not going to be able to submit my assignment. Oh, I didn't realise that was there. Sorry, I just realised I forgot to put today's, where are we? Materials 236. In case anybody needs to go to the YouTube channel. Does anybody have any questions about what I've just talked about the assessment and using WebWork? The other thing is, on this page it's saying that the midterm is due, and that's not true. Like I said, next week I'm going to release it. That date in there is just for me to remind me that I need to have released it by then in order to have time to work through everybody's midterms, because I think there's 20, 25, 24 of you. So that means I need to spend 15-20 minutes with all of you. That takes a bit of time. While I'm at it, I'll remind you of this next time as well. But there's a place to book midterm here. So instead of general consultation, select midterm. And I think I'll have to. Oh no, that's probably okay. I've made some times available towards the end of March. I may pull that back a week as well, but I'll figure it out and let you know next week what the details are. Okay, let me go back to there. So today's session, review mesh analysis. We talked about that for the first time last week. We haven't actually applied it. I do want to talk, like I said in my talk about web work, about super meshes again. And then I want to do some work on tutorial 2, which has both mesh and nodal analysis. And then the new topic for today will be another algorithm. And whereas mesh analysis uses mostly Kirchhoff's voltage law, nodal analysis uses Kirchhoff's current law in order to put together a system of equations that describe how the circuit works, and then you can solve those equations the way I showed you last time on the calculator. I probably won't use the calculator again. I needed to show you just that but it's, as you saw it, the focus on this camera isn't great for close work, and I don't know how much use it was, but I did have a simulator for the TI-83, I think, on my computer, but the free period ran out, and now they want me to pay for it more than what I could buy a calculator for, which seems a bit odd, given that I think it's something that sells their calculators. Anyway. Okay. Any questions? So let's go back to last week's notes on mesh analysis. Okay. And let's just roll all the way back. Right. So that's the algorithm. An algorithm is just a sequence of steps that you've got to take, right? And the first one is, once you've got a circuit, you assign the mesh currents. And by assign the mesh currents, there's a few things you've got to remember. One of them, what is a mesh? A mesh is a loop that doesn't cut a branch. I don't think I talked about branches yet. A branch is a circuit element. A loop is a closed path through the circuit that doesn't go back on itself. Okay, so a mesh is a very special sort of loop. Let me just write those down. So the new one was branch, and this is really just a circuit element. Okay, and then the loop was a closed path through the circuit. doesn't cut itself. And let's be explicit. And then a mesh is a loop that doesn't cut a branch. And then the other one we talked about that isn't directly relevant to mesh analysis is a node is an area of constant voltage. The funny thing about nodes is even though it's an area of constant voltage, right? Oftentimes when you have, right, an area of constant voltage like that, I actually usually just draw it like that, right, as a dot. And you'll see that when we talk about mesh analysis. But the whole part, the whole connected area of wires is the node. Okay, so first thing is to, as I said, assign the mesh currents. So now we've reviewed what a mesh is. And then identify any super meshes. And we did talk about super meshes last week briefly, but just to remind you, where you have a current source that has more than one mesh current going through it, that is when you require a super mesh. Okay, because...
Excuse me, Professor.
Yeah, go ahead.
Do both mesh currents need to be moving in the same direction or with the same...
No, so that's one thing with... it's sort of implied in the statement assign mesh currents. It's completely up to you which direction you draw those currents. It doesn't matter which way you draw them. Okay. So provided and you know there's four in this simple circuit. There's four ways I could have drawn this, right? I could have drawn I I1 going in the red direction and I2 going in the red direction. I could have drawn I1 going in the green direction and I2 going in the green direction. I could have drawn I1 going in the red direction, I2 going in the green direction. I could have drawn I1 going in the green direction and I2 going in the red direction. Right? It doesn't matter. The only thing those directions change are the signs of the associated currents. And depending on the circuit, it might have been better for me to, given that the current source is going that way, it might have been better for me to choose I1 going in the same direction and I2 going in the same direction, right? I just tend to make my mesh currents go clockwise most of the time. But that's just me. That's just a habit I've formed. It's not required. Okay, so and that's when a super mesh happens. But the other piece to remember when you're looking at current sources and mesh analysis is if only one mesh current flows through the source, then it's a freebie, because the only current flowing through that source is I1. So I1, the value of I1 has to be whatever that, maybe it's 5 amps. The value of I1 has to be 5 amps, provided I1 and the direction of the current are the same. Otherwise it'd be minus 5 amps. Okay? So you've got to make sure that you're not being given a freebie. And actually that reminds me, if you go to Professor Broderick's textbook, right, and I pointed you to the Solving Linear Equations chapter before, but there's also his, and you can see this is where I got my algorithm from, right? It's the same, exactly the same text, and there's lots of worked equations here, so have a look at those, and then there's several sections on mesh versions and worked examples for those. And then we haven't talked about dependent sources, and he talks about a shortcut. But what I really want to get to is at the end of the chapter, I believe, there is a strategy, right, for mesh analysis. And so this is on page, what page number is it? Page 65, right? And it's a strategy for dealing with all the things that I've talked about. It's, if there's a single mesh current flowing through a current source, it's a freebie. If there's a super mesh required, it talks about that, right? So there's the freebie one there. If I can figure out where my pencil got to, there it is. Right, there's the freebie one. There's the super mesh one, or a super loop. Okay. So have a look at that. And again, I do recommend having a look at Professor Broderick's textbook. There's a lot of worked equations in there. He's put quite a bit of effort into making that a useful thing. So what I thought might be good is if we can take that image and just have a quick look at it from a mesh analysis viewpoint. Right, there's the algorithm, so we'll put it up here. Okay, so there's our, now the first piece, assign the mesh currents, is done for you, right? What I'd suggest you do though is have a look and make sure that you understand what the polarities of everything is, right? So if we've got our mesh current going that way, then the VR2 from I1's perspective has a positive sign there and a negative sign there. That's always, because this is an active device, that's always a negative sign going in there. One thing to be careful of is if the circuit already defines a polarity, try and always use that polarity. In this case, it's okay, right? This is the right positive sign for I1, but you'll see when we get to I3 it's not. So you've got to be a little bit careful to distinguish the polarity of VR1 from the polarity of V out. It could be that V out is the negative of VR1 if VR1 polarities are chosen differently from the polarities of V out. Okay, that was I1. I2, right? We've got the mesh current defined already, but again, I suggest you have a look at what that means. So here's VR2, and you'll notice that the polarity of VR2 when we're thinking about I2 is different from the polarity of VR2 when we're thinking about I1. That is okay, that is normal. It's just can be confusing. Right, and then this is another battery, so we can't choose the polarities there. And then here's another passive device, so that's our passive sign convention selection for the voltages there. And then I3, right, we go around here and like I said, now we've got a different VR1 polarity from the polarity of V out. That is okay, we've just got to make sure we don't confuse the polarity of VR1 with the polarity of V out. And then here we go in here, that's plus, that's minus. This is an active device, so its polarities don't change. Okay, so that's the first step, and I'll just use a circle to say there's no super meshes in this. There's no current sources, so we don't get any freebies. We don't have the super mesh issue, so that's okay. Then use KVL on each mesh current. So let's try and use KVL on each mesh current. Let's start with I1. So KVL for I1. Well, we're going into the negative side of V1, so it's minus V1, and it's going to be plus VR1, and then plus VR2 equals 0. Okay, so that's KVL for I1, and then KVL for I2. Well, that's going to be plus VR2 plus V2 plus VR3 equals 0. And then let's just scoot up a bit, not too much. And then KVL for, let's just give ourselves a little bit more room. And then KVL for I3 gives, now we're going into the negative side of V2, so minus V2 plus VR1 plus VR4 equals 0. Okay, so that's applying KVL on each mesh current. Then we replace all of the voltages with either the number, if it's a voltage source, or the Ohm's law equivalent, which will give us the equations in terms of the things we're after, the currents. Right, so we use Ohm's law, V equals IR. Right, and I don't have any numbers for this, so I'm just going to keep V1 and V2 as V1 and V2. So that's going to be minus V1. VR1 is going to be R1 times I1 minus I3. Right, so R1 times I1 minus I3. And VR2 is going to be R2 times I1 minus I2. And then that whole thing equals 0. The I2 equation, VR2, from the perspective of I2, VR2 is R2 times I2 minus I1. V2 we don't change because we don't have a number. VR3 is just I2 times R3. There's no other current flowing through R3. And then V2, again there's no number, so we keep that. And then plus VR1 from the perspective of R1, from the perspective of I3, the voltage across R1 is I3 minus I1 times R1. And then for VR4 there's no other current, so it's just I3 times R4. And it's not a 6, it should be a 0. And it's hiding behind my head so you can see what I wrote. There we go. Okay. Any questions so far?
What does B sub 0 represents under R1?
Sorry, what does V sub 0? Oh, so yeah. So let me explain that. So so the question is, what does this mean? V sub 0 is the output voltage, right? Oftentimes the whole purpose of a circuit is to generate a voltage for somebody else to use. And this particular circuit, the reason for its being is to produce V out, V sub 0. Or it's actually an O rather than a 0. Okay? So the question is actually asking, what is V sub out? What is V sub O? Okay? And then let's just go back to our algorithm again. Maybe, here we go. Right, so we've used Ohm's law to express the resistor voltages in terms of the mesh currents. And then the last two things are to distribute and group like terms, plug the values in and solve the system. And let's just go back and do at least step 4. I won't have any numbers, so I'm not going to be able to solve the system as such. Now normally what I do is I get all the constants on the right hand side and all the i's on the left hand side. So here our constant is v1. So if we add v1 to both sides, that brings it over there. And then we look at, we've got I1, I2 and I3. So we've got R1 plus R2 times I1, right? R1 plus R2, and there's I1. And then we've got minus R2 I2 and minus R1 I3. Okay, and then for I2's equation, we're going to subtract V2 from both sides, and then we get a minus I1 R2, right? And it looks like there's only R2 left, so I2 left, so it's plus R2 plus R3 times I2. Okay, and then for the last one, again we've got a constant, so we add V2 to both sides, and then we have a minus R1 I1, and there's no I2, so it's just plus R1 plus R4 times I3. And I'll just move that over a bit. So now we can put all of that into a now remember what I'd suggest you do when you're writing this down is to remind me and to remind you about how you're going to use your calculator, if you're using calculators, is to write down RF, right? Remember, that's my preferred method of solving equations on the calculator, because it means I only have to deal with one. In this case, it'll be a 3x4 matrix instead of one 3x3 matrix and one 3x1 matrix. Actually, before I go there, let's just write out the matrix equation. Okay, so the matrix equation looks like, so we've got R1 plus R2, we've got minus R2, we've got minus R1, and that multiplies, excuse me, I1, I2, and I3, and that equals, at the moment we've only done the first ones, it's just V1, and then we've got minus R2, R2 plus R3, and there's no I3 term, and the voltage is V2, or the constant is V2, and then down here we've got minus R1, R1 plus R4, so there's a 0 there, R1 plus R4. Be careful that, right, this is I3, be careful that you don't inadvertently fill in a space in the matrix that should be 0. And then on this side is V2. Actually, I forgot the that one there is actually a minus V2, and this one is the plus V2. Okay, and then that's the equation. Excuse me. That's the equation. But when you plug it into your calculators, you want to do it slightly differently, right? So you want to make an augmented matrix that combines A and B, right? And so B is here, and then A just gets put, sorry, that should be a 1. Okay, but you'll have numbers there that you can fill in, and once you solve that RF equation, just close the bracket there, or the parenthesis, and yeah, that's the way to approach the first question in the homework assignment. Let's just have a quick look through some of the other questions maybe. Oh, I got logged out. So there's problem 2, right? And this is what it normally looks like, right? Once you haven't entered anything. And if I check my answers, it'll come up with some suggestions, and it'll highlight these in red if they're wrong, right? And maybe it wanted an equation in there, right? And they're the wrong equations, right? You can check answers again, and it's not telling you, hinting that you've got something wrong in the formatting. Now it's just saying, oh, that's wrong. Okay, and that's the format. And you can submit answers, but I think it'll keep letting you submit answers. If it doesn't, let me know, and I'll fix it one way or the other. So that's for this one. Remember this is a current source, and you've got only one mesh current going through it, so that's a freebie. Problem 3. Problem 3 is a bit harder because problem 3 has a dependent current source. And it's even harder still because that dependent current source has both I1 and I2 going through it. So we have to do we have to use a super mesh approach, right? And whereas normally we'd have a Kvl equation for I1 and a Kvl equation for I2, because we do a super mesh approach, we have to do a Kcl equation to make, in this case it would be I2 minus I1 equals Is, right? Because we've got we've got the I1 going that way and I2 going that way, and they both have to, well, because of the direction, it's I2 is going in the opposite, is going in the same direction as Is, and I1 is going in the opposite direction, so I1 is negated. So I think, let's just check, the answer for this one is probably that. Yeah, okay. Because we've got that super mesh, our two Kcl equations, one for each mesh, translates into one super mesh equation, Kvl equation, and one Kcl equation. Okay, that's that one. And here's another super mesh problem. This one's probably a little easier because the current source is no longer dependent, right? So it doesn't depend on anything. Let's just go back to the previous one and see what IS depends on. Right, there it is. IS depends on 4ix, right? 4ix, and there is ix there. Right, so ix is equal to I1 minus I3. So IS is 4 times I1 minus I3. And then the super Kvl equation has to go around this loop in order to avoid passing through the dependent source. Remember, the whole reason we don't want to have a Kvl equation for current sources is because we've got no idea what the voltage drop across a current source is. We don't know. The only way we'll know what the voltage drop across a current source is after we've solved the equation. Right? The only thing we know about the current source is what current is flowing through it. And because it's an active device, there's nothing other than analysis that will tell us what the voltage drop is. Okay, let's just have another quick look through what's happening. Okay, this is combining the two big issues we have. One of them is that there's a super mesh requirement, right? And the other is that now it's a dependent voltage source. And again, I think because of that super mesh, we probably only have 2 and 1. And let's check my answers. Yep. And then it asks you for the super Kvl, Kcl. And then the equation, and then what's the output voltage. In this case, the output voltage is defined as here. Everybody okay with that? Yeah, so where are we? What is that one? That's my review of mesh analysis. Let's just quickly go through the slides. That's from last week. And there's a more complicated one. And that's the super mesh stuff. And then there's some other super mesh examples that we should maybe go through. I think what I'll do is I'll just quickly go through these two super mesh examples. Then we'll have a bit of a break, and then we'll come back and we'll have a go at the tutorial. Let me just check the tutorial. I think I made that available last week. So there's I think there's 4, 1, 2, 3, 4 mesh analysis questions. And then we get on to nodal analysis, which I want to start covering later today. But let me just go back and talk about super mesh again. Okay, so here's a really relatively simple circuit. It's got two mesh currents defined, I1 and I2, and it's got a voltage source and a current source, both of which are independent. They don't depend on anything else. So with this one, let's just get a color that we can see. There we go with blue. Right, the issue here is that I1 and I2 both go through IS. Right, so one equation that we could come up with is 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 equal to I2 minus I1. Right, so I2 is flowing in the same direction, and I1 is flowing against IS, so I1's going to be negated. So that's going to be our Kcl equation for this circuit. And then the Kvl for the super mesh, remember we have to go around avoiding the current source, but we still have to use I1 and I2, right? So I1 and I2 are going round that way, so our polarity for I1 is like that, and our polarity for I2 is like that for the voltages across R1, R2 and R3. So then our super loop equation, right, the green one, is going to be minus Vs, right, because we're going into the negative side, plus I1 R1 plus I2 R2 and plus I2 R3. And because it's a Kvl equation, we write that should be identically 0. Remember, Kvl is the voltages around a loop must sum to 0. If they don't sum to 0, then we can effectively create free power, free energy. Or we can get as high a voltage as we like just by keeping on going around the loop. We keep adding. If the loop gives us 20 volts, then we can go around again to get 40 and 60 and 80 and 100, which is not really reality. So Kvl sets the total voltage to 0 around the loop. Okay, here's another super mesh example, and this is kind of nice because it's got two current sources, one of which gives us a freebie and one of which means we need to do a super mesh. The freebie is this one, right? We've got I1 and a 4 amp, so this one tells us that I1 directly equals 4 amps. Okay, and then here we've got a current source with two mesh currents flowing through it. So that means our Kcl equation is that I2 minus I3 equals 5 amps. Okay, we have three unknowns in this, I1, I2 and I3. That means we need three equations. We've found two of them. Thankfully, one of them was really easy. I1 equals 4 amps is an equation. It's just a really easy one. So the most complicated equation now, and I should have done this before, right, is to figure out what the polarities are. So I1 is going around like that. I2, let's go with green, is going around like that. And I3 is going around like that. Okay, and the super loop that we need to do to avoid the current source with two mesh currents going through it is like that. Okay, so that equation is going to be minus 10 volts, right, because we're going into the negative side. Now the voltage across R1 is R1 times I2 minus I1. Right, because I1 is going in that direction. And, right, those things are opposite. And then the voltage across R2. Now maybe I should have written down the Kvl equation first, right? The just the voltages. That I'm going directly to the third step, if you like. So the voltage across R2 is R2 times I3 minus I1. And then the voltage across R3 is just R3 times I3. And again, that whole thing has to equal 0. Now I just want to make sure that I'm not going to, that this one isn't the same as one of the tutorial questions. I do want at least the numbers on the tutorial questions to be different. 8Vx, 6Vx. So it is a little different. Okay, so I thought it might be instructive to just have a look. This is a second midterm question from fall 2018, and it's similar to what you'll get in your second midterm, not the one that's coming up, but the one after that. Okay, and it's the complicated thing about this one is that there is a dependent voltage source here, right? Vs2. Remember, that's not 6 volts. That's 6 times Vx, and Vx is defined up here. Okay, so let's draw some mesh currents, and I'm just going to do my usual trick and have I1 going that way, and that means my polarities are like this, and I'm going to have I2 going that way, and that means my polarities are like this. notice that we're asked for V out, but I've decided that VR5 has the opposite polarity of V out, just because of the way I've chosen my I2 direction. Okay, so that's the first step. Assign the mesh currents, and I also suggest you go through and draw the polarities of all the components. The next step is to write down the Kvl equation. Okay, so for each mesh, so the Kvl equation is going to be VR1. So let's just write that out. Kvl for I1 is VR1 plus VR2. Sorry, my tablet's moving around a little bit. Plus R3, sorry, that's just VR3 minus, because we're going around that direction, minus VS1 equals 0. And then the KVL for I2 is going to be 10. Well, let's just write it out as VS1, and it's going into this side now, so it's plus VR3, remember, which is a different VR3 from this VR3 because of the polarity switch, plus VR4 plus VR5 plus VS2. Again, we're going into the plus side, and that whole thing equals 0. Then apply Ohm's law. So VR1 is just R1 I1. VR2 is just R2 I1. VR3 is just R3 times I1 minus I2. And then our VS1's on the other side, so that's just 10 volts. Okay, then our VS1, and I'm going to put my VS1 on the other side, so it's minus 10. And then VR3 is going to be R3 times I2 minus I1 plus R4 times I2 plus R5 times I2 and then the tricky bit, it's going to be plus 6Vx. Let's just quickly look at what 6Vx is. Vx is equal to 3200 times I1. Right, because we've chosen the polarity of I1 to be the same as the polarity of Vx, so that's 3200. So 6Vx is equal to 6 times 3200 I1. What's that? That's 18,000 plus 1200, so it's 19,200. Okay, so let's just write it out as Vx is R2 times I1. So that's 6 times R2 I1, that's our VS2. Okay, and now we can start plugging some numbers in there, although maybe we should do the next step and distribute and group like terms and then put some numbers in. Okay, any questions about any of that? That was a quick review of mesh analysis and with a bit more emphasis on the super mesh issue.
I have a quick question. If I1 was chosen in the opposite direction, then Vx could be negative 3200 I1.
That's correct. That's the issue. You've got to, if you don't want to confuse yourself, I suggest you try and choose your mesh currents to flow into any polarities I've given you already. In this case, Vx has the same polarity as Vr2 from the I1 perspective, but you'll notice that the V out I've chosen to be the opposite polarity, or I've chosen I2's polarity to be the opposite. I'd suggest maybe I should have chosen I2 going the other way, just to make sure that the polarity of VR5 matches the polarity of V out. But what you said is correct. The only difference is that there's a sign change. And the biggest mistake I make, the biggest mistake you will make as a student body, is signs. It's the easiest thing to get wrong, and it tends to be a little bit confusing and a little bit tricky. It's simple to fix, but it's the most common mistake I see in this course is just getting the sign wrong. So yeah, that was a good question. Okay, any other questions? If not, let's do our usual trick and have a bit of a break now. I'll set it up for 10 minutes. And when we come back, we'll have a look at the tutorial, and I'll split you up into breakout rooms, and I'll assign each breakout room a separate question from the tutorial. Okay. So let me bring up that and my 10-minute timer, and we'll go with that. And I'll see if I can turn off Mini-Me. Okay, and we're back. After that brief break, does anybody have any questions? Okay, let's see if we can set up some breakout rooms. And so let's actually, before we do that, let's have a look at the the tutorial sheet. Right, you should have access to the tutorial sheet. Let me check. I think I uploaded it here. It's available in Blackboard. It's available in OneNote. Okay, and there are 4 questions. On mesh analysis, and I think 4 on nodal analysis from memory. Let's just check. There are 4 on nodal analysis. Yes. So what I'd suggest is we do the usual thing. I'll set up 4 breakout rooms, and the top in the list in Discord will do question 1. The next one will do question 2. The next one will do question 3, and the final, the bottom one, will do question 4. Okay with that? So let me see if I can figure out how to do 4. I think that's the way to do it. So this breakout room's going to be doing question 4. Okay?
Okay, thanks.
Hi, this breakout room's going to be trying question 3. Hi, this breakout room's going to be trying question 2. 2. You're second on the list by the looks. Hi, this breakout room's going to be trying question 1.
That sounds good.
Okay,
Sounds good.
I'll leave you alone for a few minutes.
Okay.
Okay, so we're doing question 4 here, right? Now this along with question 3 are one of the tougher ones. So have a look at it. It's very similar to the example that I did. The main difference is that the dependent source is in a different place, but we've still got the dependent source being 10 Vx, and Vx is up here. So remember the steps. 1, define the mesh currents. 2, write down KVL. 3, use Ohm's law. 4, distribute and group. And 5, profit. Well, solve. So this, along with the question 4, is one of the tougher ones. Okay, so let me just erase what I had there before. But the idea is pretty similar to the example that I did in class. Right, so the first thing you've got to do is define the mesh currents. Then write down the KVL or KCL if there's a current source. Then use Ohm's law to get those KVL equations in terms of currents, which are the unknowns. They're the things we're trying to find. Then distribute and group like terms. And finally, profit or solve.
Yep, sounds good.
Okay. Yeah. Keep losing Discord. There we go. Hi, looks like a few people dropped out of here. Is that right? Hi, looks like a few people dropped out of here. I think it was supposed to.
Hello.
Hi, how's it going? Any thoughts?
It just takes me quite a while because I'm distributing all the terms and have
That's
to do
okay.
the matrix, but it's working fine because, like you said, it's the same as kind of what we did, just a little reversed.
Mm-hmm. Okay, cool.
And there's no super mesh in this either, right? I mean,
No, none of the examples I've given in the tutorial have a super mesh. I tend to leave them for the homework, just because they do tend to be a bit more confusing and take a little bit more time, at least initially. Once you get used to them, they're okay. But
okay.
okay.
Yeah, but it's going well. Thank you.
Okay, I'll go check another group. Okay, how's this group going? Any stumbling blocks or problems?
I'm just in the process of plugging in the systems into my calculator.
Okay.
So, I think so far so good.
Okay, very good. I'll give it a few more minutes and then I'll call everybody back. Okay, how's this group going with question 2?
Yeah, still working on it.
Okay, that's all right. I'll give you another few minutes, and then I'll call everybody back to the classroom, and I'll see if I can get somebody to from each group to give us their solutions.
A really quick question on problem number 2. R4 is like minus 12 volt, right? Because it's going in a minus power supply. I mean power source, sorry. Battery, power, battery, minus battery.
Well, it depends on, let me just share my screen. This is for question 2, right?
Yeah, yeah.
So here let me just get rid of my previous scribbles, right? Here this top plate is the positive and the bottom plate is the negative. Okay, so if you, depending on which way you're drawing the current, right, if you're drawing I3 to go that way, then you're going into the negative side, right? So yes, it'll be a negative 12 volts from that perspective.
All right, thank you.
Okay. You're welcome. Let me just go check on the first group.
And now where I'm struggling is putting these together into a matrix.
Okay, I heard the word struggling just as I came in. So what's the issue?
We have our KVL equations. We just finished and went over those. And I'm just trying to put them into a matrix.
Okay. Let me just put that up. Okay, so this is question 1, right?
Yeah.
And I think I drew those colours on there before. So, right, I'll oops, that's too big. Let's make it, maybe that's way too big. Why is that so big? I don't know what I'm doing wrong there. Let's try a different colour. Wow. Sorry. So that's I1. It's just so thick, and I'm not quite sure what I'm doing to make it so thick. That's I2. And that's I3. And I wish it wasn't quite so... Oh, it's a marker. That's why it's not a pen. That's the difference. Okay. And so you want to go around here and...
Sorry, actually I did put it into the matrix. This is what I got, but I don't know if it's right though.
Sorry, what was
So
that?
for the current, I1 I got a negative 1.837. I2 I got negative 1.70. And I3 I got negative 0.8.
Okay, does anybody see that that's correct or not? So let's just think about the sign to start with, right? Normally you'd think about the current flowing out of the positive terminal of an active device, right? And the fact that our I1 is going into the positive of our active device suggests that maybe the I1 should be negative, right? Because in reality the current is flowing out of the active device. So that, at least the sign of your answer sounds correct. Okay, I think if you're finished, I think other people will be, so I'm going to try and call everybody back. And I've forgotten how to do that, so I'm just going to figure that out. Let's call back. Okay, I think we've got everybody back now. Let me just turn me back on. There we go. So let's start with question 1. I think there's at least one solution to question 1. Would you mind one person from that group, at least let's walk through the steps, right? The steps are, well, we've already defined the mesh current, so we're done with that one. And but let's go with the next one, which is apply KVL. Can somebody from group 1 talk me through KVL for I1, I2 and I3?
For the KVL for I1, it's just the, so first we'll write out the equation, voltage source plus VR1 plus VR2 equals 0 for the initial loop on the left.
Right, so this is R1 and this is R2, right?
Yeah, hold on, let me switch back to your stream. Yes, yep, R1, R2, 4, R5, just left to right for simplicity's sake.
Okay, so R3, R4 and R5, just...
Yeah.
Okay, cool.
And then for I2, the formula was VR2 plus VR3 plus VR4 equals 0.
Looks good to me. And then...
I3, pardon?
I was just going to say KVL for I3, yeah.
That's just VR4 plus VR5.
Okay, that looks pretty good. So can somebody else from the group tell us what the next step is? So the next step is apply Ohm's law. Somebody...
Right. For the KVL 1, 10 5I1 6 into parentheses I1 minus I2 or 0.
Okay, sounds good. So next one, KVL for I2.
All right, so for the next one, for the next one, I go x into parentheses I2 minus I1 plus 2I2
Yep.
plus 4I2 minus I3.
I2 minus I3, and that equals 0. Very good. Okay, and the last one.
Yeah, okay. So the last one is 4 into parentheses I3 minus I2 plus 4I3 equals 0.
Okay, very good. So the next step is to distribute and group like terms, and I'll just take it from here if that's okay. So I'll just so that means we have 11i1 minus 6i2 equals minus 10. Right, subtract 10 from both sides, and then we've got minus 6i1, and there's 6 and 2 and 4 i2, so that's plus 12i2, and there's minus 4i3, and there's no constant, so it's just 0. And then this one, there's no i1, there's a minus 4i2, and there's an 8i3, and again there's no constant, so it's 0. So then we can just write that out, and I'll write the full matrix equation. It's 11 minus 6 minus 6, 0, times I1, I2, and I3, and that equals 10, 0, 0. And then here we've got minus 6i1, 12i2, and minus 4i3. Here we've got 0i1, minus 4i2, and 8i3. And from there we can say RF of 11 minus 6, 0, 10, minus 6, 12, minus 4, 0, 0, minus 4, 8, 0. And I haven't fired up MATLAB yet. Let me do that. Like I said, you should be able to do that relatively easily in your calculators. But I don't see me doing it on a calculator and showing you is going to help because of the focus on the webcam isn't great, at least for close work. I should have fired up MATLAB a little earlier so we could actually see it. Just thinking about it. There we go. Still thinking. So let me just put that over there so we can see everything. And our A is equal to 11 minus 6, 0, 10, minus 6, 12, minus 4, 0, 6 minus 4, 8, 0, and then RF of A, and let's just make it a bit bigger so we can maybe see it a bit better. Okay, so we've got our first three columns just being the identity matrix, and then the answer we get, let me just move that over to here. So the answer we get there, ooh, that's interesting. Did I do something wrong? So the answer, I'll just write down the answer and we'll check them then. the answers I got were I1 equals 1.087 amps, I2 is equal to 0.3261 amps, and I3 is equal to minus 0.6522 amps. And that is confusing me a little bit, because like I said earlier, I was expecting to see a negative current on I1. So just an aside, when you write down your numbers, I recommend you write down 4 significant figures. Okay, I'm okay with the final answers being in 3 significant figures, but all intermediate values should be in 4 significant figures, because it tends to the accuracy in the final answer. If you've got intermediate values using only 3 significant figures, the answer at the end can then only be accurate to 2 significant figures sometimes, which I don't think is accurate enough. So can anybody see what I did wrong there?
Did you use -10 for the output voltage, or for the, sorry, not output voltage, but in that row?
I did not. You picked it exactly, right? Thank you. Right, so the issue is I put +10 there rather than -10. So let's, so what's that? That is A14. Let's just check that that's... Okay, something's gone. For some reason, it's not letting me type there. Is there another? Yeah, so that'll be the reason, right? So that is the command window. I'm just going to copy that. If it'll let me, it won't let me copy. It's not letting me put in anything. Sorry about this. I'm just going to kill it again. But yeah, so the issue was that I miswrote it down here, right? So there should have been a minus sign there because of that. So,
And Professor, there is third equation. There is no I1, I guess.
there's no I1.
Can you go a little bit back?
Yep.
On the right. Yeah, there is 0, not 6 at the. third equation.
This one here, yeah, that's my bad writing. It's a 0.
Oh, okay, thank you.
That's okay. Yeah, so that should be a 0. And then I suppose the other one looks a bit like a 6 as well. So that's just my bad writing. Like I said, my tablet seems to be wandering all over the place this morning for some reason. Makes it a bit difficult to write sensibly. Okay, so that's the first question. Let's have a look at the next one. And let me just erase my scribbles from last week. Or maybe it was from earlier today. So can somebody from the second group talk us through how you would do this one? And this one, remember, we've got our define, KVL, Ohm's law, distribute and group like terms, and profit. We'll solve. Can somebody from the second group talk us through this one? No? Nobody? I didn't. Okay, go ahead. Is somebody wanting to say something? Let me just, I've forgotten who the, I think I took a screenshot of, that's one problem with the, there's one problem with the breakout rooms. So, second group was Christian, David, Drew, Giovanni, Mehul Kumar, and Ryan. Does any one of you guys have an approach? At least write down define the mesh equations or the mesh currents. Dead silence. Mehul Kumar, do you want to have a go?
Yeah, but I'm a little bit confused right now. I can start with the I1.
Yeah, let's just start simply with the defining the mesh currents. So how did you define the mesh currents?
All right, so first equation gonna be VR1. If you go in a right side direction, yeah.
Like that. So that's I1.
Yep.
Okay. What about I2?
Right.
In this
yeah, I take the same direction. Yeah.
same direction. Okay.
Yeah. And third is also the same.
Okay. Sounds good. And I'm just going to go through, and like I said, I prefer putting the appropriate polarities on. All right, so once we've got those on, at least on all the passive devices, the active devices, we've got to stick with their directions. Okay, what's next?
All right, so VR1 plus minus VR2. Oh, sorry, plus VR2. It's equal to 0.
Okay. So
And
there's another device here, right?
right, so probably there's minus, not 0, but there's like in a minus direction.
Right. So the issue is that we're trying to write our KVL equations, right? Our Kirchhoff's voltage law equations, which we need voltages for. And this is a current source.
Right.
Right? So that means we can't write an equation in terms of voltages because we don't know what the voltage across here is. However, it's a current source and there's only one mesh current going through it. Right? So what we can do is we can write a Kcl equation that says effectively just I1 equals IS. Okay?
Yeah.
So that means we immediately know that I1 is 400 microamps. Okay?
Yeah.
So let's move on to the next KVL equation for I2.
Okay. It's VR2 plus VR3 plus Vs, yeah, equal to 0.
Yep, that's right. Okay, and then the I3 equation.
It's minus Vs plus VR4 is equal to 0.
Exactly. Okay. Can somebody else from that group do the next step? So we've done the KVL equations. Can somebody else do the Ohm's law substitutions so that we get the equations in terms of the currents? We've already got the first one. That was a freebie because there was only one mesh current going through a current source. Somebody talk me through this one?
So that one could be R2 times I2 minus I1. Plus R3 I2
Sounds good.
plus 12 equals to 0.
Sounds good. And then the last one, yeah.
Last one could be minus 12 plus R4 I3 equals to 0.
Okay. So we're just about there. So that's the Ohm's law one. Now I think I'll take it from here. The distribute and group like terms. For this one we get minus R2 I1 right, plus R2 plus R2 plus R3 I2, and I'll take the constant over the other side, and then there's not really anything to distribute here, so it's just R4 I3 equals 12. And then our matrix equation, well, do we need a matrix equation, right? We've got, in fact, before we do that, let's just plug in some numbers, right? So in the first case, we've got R2, which is 4700. So it's minus 4700 times I1, which we already know the value of, which is 400 by 10 to the minus 6 amps, right? Remember, microamps is 10 to the by 10 to the minus 6. And then R2 plus R3. R2 is 4700. So what's that? That's 8600. I2 equals minus 12. And then our last equation, R4 is 4700, so we can actually just write that out as 4700 I3 equals 12, and we don't even need a matrix equation, right? So that's our I3, and we don't even really need a matrix equation here because there's only one unknown. So let's just write that out again. We've got, so that becomes 8600 I2 equals minus 12 plus 4700 times 400 by 10 to the minus 6. So I2 equals minus 12 plus 4700 times 400 by 10 to the minus 6 on 8600. And let me just fire up MATLAB again. I don't know what I did to stop it taking input before. Hopefully it's restarting it all. So did anybody get some numbers for I2 and I3 while we wait for MATLAB? I suppose I could okay, so it's 12 on 4700. It's I3. Right, so it's 2.553. Let's just get the right color. 2.553 milliamps. And then let's scroll that over and see if we can plug that in for I2. So I2 equals minus 12 plus 4700 times 400 times 10 to the minus 6 on 8600, and I'm just going to multiply that by 1000. Right, so it's minus 1.177 to four significant figures. And that is not amps, actually, that's milliamps because I multiplied that by 1000. that all okay? Does that all make sense for everyone? Any questions about how we approach that?
Just answering the question. Oh, sorry.
No, go
It
ahead.
asks for it asks for I sub x. What
I
would be
sub
the
x.
answer there?
Right. Good catch. And that's something that a lot of students do, and obviously I do it too. There was somebody else wanting to speak? Did you have another issue?
No, I was going to say the same thing.
Okay, good. You're on the ball. You're more on the ball than I am. So let's have a look at what Ix is, right? That's what we've got to find. Ix, because it's defined going in that direction, right? It's going against I2, but in the same direction as I3. So Ix is I3 minus I2. And let's see what MATLAB tells us that is. And at the moment I've put my I3 and I2 in terms of milliamps, so if I just do I3 minus I2, that should tell me what it is, and it's 3.730 milliamps to 4 significant figures. And 3.730 milliamps. Does that make sense? Okay. Let's move on to question 3. Now the question 3 and question 4 are a little harder. They're only a little harder because of the dependent source. It just makes it a little trickier. Once you're used to it, it's okay, but the first time you come across it. So can somebody start us off and define the mesh current directions?
Sure. So I had I1 in sort of the left half and I2 in the right half. I had them both going both going clockwise rather.
Both going clockwise. So like that.
Yep.
That's I1, and that's I2. Okay.
Yep. And so for I1, doing KVL, you have the voltage through the 5 ohm resistor, which would be 5 times I1, plus the next resistor, which is 4 times I1, and then the 4 ohm or the middle resistor, I guess you'd call it, which you'd have 4 times I1 minus I2 in this configuration. And then since you're going sort of backwards, I guess, through the voltage source, you consider that a voltage drop, and you say plus 12, or you're going plus to minus through it. And that'd be 0.
Okay, and then for I2?
And for I2, starting with the voltage source, you'd be minus 12, plus 4 times going the opposite direction now, so I2 minus I1. And then going around the circle, it'd be plus 2 times I2. And for the 8 ohm resistor, it'd be 8 times I2. And then for the dependent voltage source, it would be still going minus to plus. So it'd be minus 8 times Vx, which is the R2 resistor, which is be 4 times I1. And I'm at equals 0.
That whole thing equals 0. Looks pretty good to me. Okay, so let me take it from there. So our next one is so what we did then is we sort of did both of those steps in one hit, right? We applied KVL, but we, instead of just writing down VR1, VR2, VR3, etc., we wrote down the Ohm's law equivalents every time. And then so our distribute for I1, we've got 1, so 5, 9, 13 I1 minus 4 I2, and that equals minus 12. And then we can distribute I2, and we've got a minus 4 I1 and a minus 32 I1. So it's a minus 36 I1. And there's 4 I2, 6 I2, 14 I2. So plus 14 I2. And that equals, if we take the 12 on the other side, the minus 12 on the other side, it becomes plus 12. Okay, so now we have our equation, or our matrix version of the equations.
Could you take a step back and re-explain the 8 times 4 I1 in the KVL for I2?
Sure. So the VS2.
Oh, no, I see. It's voltage based off of that resistor. Sorry, I was just confused on that.
Yeah, exactly. So it's 8 times Vx. This isn't 8 volts. It's 8 times Vx. And Vx, we're using the right polarity for I1 and Vx, the same polarity for I1 and Vx. So that's going to be 4 times Vx by itself is going to be equal to 4 times I1. So 8 Vx is 8 times 4 times I1, which is how I got that. Okay? No, you're very welcome. That is the most confusing thing about this problem. Okay, so there's that. Let's see if we can plug that into MATLAB. And so it's 13 minus 4 minus 12 minus 36, 14, 12. And then RF of A. We do have it's always good to check that you get the identity matrix in the first part of the equation. And then we've got minus 3.158 and 7.263 to 4 significant figures. So that tells us that I1 and I2 equals, what did I say, minus 3.158 and minus 7.263 amps to 4 significant figures each. Okay, so that's question 3 done. Now question 4 is arguably the hardest, and the only reason it's a little bit harder than question 3 is because now we have more realistic resistor values. Question 3 just has, 4 ohms and that sort of thing, whereas now we've got kilo ohm resistors, and that's a more usual resistance value than 4 ohms or 6 ohms or 2 ohms. So can somebody from the fourth group talk us through this?
Yeah, I can go through.
Okay.
So I did clockwise I1 and I2.
Mm-hmm. So there's I1, and I'll just change colors for I2. Both clockwise. Yep.
Okay, and then KVL for I1 is I did R1 times I1 plus R2 times I1 plus R3 times I1 minus I2
Sounds good.
minus 10 Vx equals 0.
Okay.
And then for KVL for I2, I have positive 10 Vx plus R3 times I2 minus I1 plus R4 times I2 plus R5 times I2 plus 12 equals 0.
Okay.
And then I just, before I put the numbers in, I kind of just defined like B of BO is 5,000 times I2, and Vx in this case is 2,000 times I1 according to our KVLs.
And then Vx is 2000 I1. Sounds good.
So then I just I did all the like terms, and I got for KVL for I1. Do you want me to talk it all out, or just give you the final equation?
And well, just give me the equation with all the numbers in it.
Okay.
Okay.
So so combined is negative 16,000 I1 minus 1,000 I2 equals 0. And then the second one, I have 17,000 I1 plus 12,000 I2 equals negative 12.
Okay.
And then I just kind of solved it algebraically, and I got oh yeah, you could do that too.
I'll just write out it should be 16,000 and minus was 1,000 I2.
Yes.
And 0, and then 17,000 and 12,000 and minus 12. Okay, and then what did you get for the answers?
So for I just got, all I found was I2 and VO because that's really all we needed for the answer.
Okay.
But but for VO I got 5.486 volts.
5.486 volts. Okay.
And I2 I think it was negative 0.001097 amps.
0.01997.
1097.
1097.
Right.
Amps. Okay. I would tend to put that in terms of milliamps. I'd make it minus 1.097 milliamps. Just because I tend to prefer having, not having so many leading zeros in the number, but that's okay. Okay, let me just plug those numbers in here, right, just to see what all of them were. 16,000 minus 1,000 and 0. I shouldn't have written the I2 there. 17,000, 12,000 minus 12. And let's multiply that by 1,000 maybe to see it a bit bigger. No, that doesn't help. I've got to do it individually. So this is I1, I2. And we want I1, I2 of 1, 3 to get I1. So that's pretty small. right? That's 68 microamps. So for I1, that's 68 microamps. And let me just bring it back and get I2, which is going to be and again, so I'd probably write that as minus 1.098 to get the right, just to round up the 7. But yeah, you got the right number there. And it's milliamps. Okay, that looks good. Okay, I think we all deserve a break after that. Does anybody have any questions about any of the tutorial problems that we've looked at this morning? No? Okay. I'll assume that the happy humming means no, and we'll leave it there for about 10 minutes, just to go back to what I'm hoping to look at today, right? So what have we done so far? We've reviewed mesh, we've talked about super mesh, and we've done the tutorial to mesh analysis. I don't think we'll have much time to try the tutorial to nodal analysis, but I'll see how we go through when I introduce nodal analysis. Okay, so let's again, unless anybody's got any questions, let's take another break, and we can go from there.
Professor?
Yep, what's up?
Lab number 3 is due next Saturday, right? You're gonna explain everything about it, or just we can start doing it?
You can start doing it, but that's actually a good point. I really should introduce the labs. So let me add to the list of things. When we come back, I'll introduce lab 3, and that's a good point. Thank you for that. Okay. Yeah, all of the labs except maybe one, and all of the homework assignments, again except maybe one, are available now. So you have your work cut out for you for the most of the rest of the semester as far as homework and labs are concerned. Okay, let's like I said, let's leave it there for 10 minutes. I'll go with another 10-minute timer. And when I come back, I'll talk about lab 3, and then we'll jump into nodal analysis, which is the second algorithm that we're looking at. Okay, let's get started again. So I didn't mean to go with that one, I meant to go with that one. So as was brought up before the break, it'd be nice to have an intro to the lab. So let me do that. I gave an intro to the next homework assignment, which is on web work. But let's have a look at the lab. Okay, so lab 3, and let's just copy that over into here, and let's put that in here, and I might download the actual lab paper as well, and I'm going to put that just in my downloads folder. And let's add that. Oh, it didn't put the image in. No, it didn't put the image in. Okay, it's okay, it's just a screenshot of the wrong one. I want printout, and we want from the downloads folder. Okay, so this lab is about Kirchhoff's voltage law and the voltage divider, and the aim is for the student to examine the relationship between combinations of voltage drops and combinations of resistance values in a series circuit. You've got to measure the voltage with respect to a common reference point at various points in the circuit. Apply the voltage divider formula in a series circuit, and for you to actually design a voltage divider to give a desired output voltage. Okay, so let's just have a look. The voltage divider, right, is, if you've got a series circuit, then the voltage drop across each of the resistors in the series circuit is VR1, VR2, etc. And if the voltage applied to the series circuit is Vs, then the voltage drop across R1 is just, where's my drawing gone? Right, the voltage drop across R1 is just R1 divided by the sum of all the resistors in series. The voltage drop across R2 is just R2 divided by the total resistors in series times Vs, all the way down to the last resistor, call it Rx, divided by total resistance. So RT is just R1 plus R2 plus all the way down to Rx. Okay, and then here's a circuit, and we don't have any we don't actually have any voltage sources in the circuit, right? They're all, but they could be. These elements are just boxes. They could be just about anything. But the idea is to illustrate Kirchhoff's voltage law, right? And the idea is to go around the loop this way, and if we go in here, then the Kirchhoff's voltage law equation is VAE minus VAB minus VBC minus VCD minus VDE equals 0. Right? That's exactly what we've been doing with mesh analysis this morning. Let me just close that because I don't need it. And then the other thing it's looking at is it's saying, well, what happens if we define VAD, right? So the way to read all of these, right, VAD is the voltage at A relative to D, right? The voltage at A relative to E, the voltage at A I probably would have done that the other way around, relative to B, etc. Okay, so what this one is doing is it's saying, okay, I'm going to take this voltage as a single voltage, VAD, and then go around the loop again. And it's exactly the same equation, except now our the two endpoints are combined into a single VAD here. Okay, but it's exactly the same equation. So the aim is to demonstrate the four objectives, and the first one is to construct a simple circuit comprising of a single mesh with at least 5 resistors of different values. So let's fire up LT Spice and see about doing that. And I'm going to start a new blank schematic. Right, so we want 5 resistors, and we probably also want a voltage source in there, and you want to measure and record all current. So let's add some stuff to this. Right, and I prefer having simple numbers, so let's go with 10 volts, and then we can add another, we can add some resistors. Right, and I can go Control R to rotate things. And there's 5 resistors. Right, it said at least 5. And then was it F3, I think, for drawing wires? Okay, and then to get the no, I always forget the net name. I think it is. To get the ground. Right, and then F3 again to oops. To wire it up, and then we need to add our spice directive, and one option is .op1 or .trans1. For our later experiments we'll need .trans1 rather than .op1, so that's why I tend to use .trans1, so I don't have to change it once we start talking about sinusoidal voltages. We haven't chosen any numbers yet, so let's just choose some numbers, and they have to be all different. Right, Alright, and then 500, just for simplicity. So we have 5 resistors, and there's a voltage source. Let's see if that runs. Yeah, there's no errors, so it's running quite happily. And then we can, and it looks like all of my currents are flowing the wrong way. Okay, so what I'm going to do is I'm going to see if I can edit them. And I've forgotten how to edit it. Let me just kill that. That's I was editing them last time. What have I done wrong? Oh, I think there we go, finally. Right, so now we've got that one round the right way. Let's see if I can rotate that one. So that's what I got to do. Got to move. Get those things around the right way. Oops, wrong one. No, I don't want to do that. I want to move, select R4, rotate it round, put it back to where it was. It's F7. Okay, and now F2 again, no, F3 to fix up my deletions from before. Okay, so now let's run that again and check to see what's happening. I've got my current flowing in. Oop, that one's gone the wrong way. I got R3 wrong. Let's try that again. Now it's going in the right direction. Okay, so they're all going in the same direction, and I can measure them all. It's about 6.7 milliamps, but they should all be the same, right? So if I keep, for some reason, that is really bizarre. I don't know why I3 has decided to go negative. I don't think that's right, do you? Look, it's going the same direction. That's really bizarre. It's got the R3 on the top. For some reason it's decided that I3 is negative. That's just wrong. They should all be the same. Okay, be very careful. I can't see that I've done anything wrong. Let's just, oh, it might be that I didn't stop it and restart it. That's what it probably is. So let's stop the run and restart the run, because it was round the wrong way before. And now it's in the right direction, right? It was because I hadn't restarted the simulation to get for it to take on the new orientation of the resistor. So just be careful with that. Okay. What do we got? We got design and construct a voltage divider that uses only 2 resistors and takes in 15 volts. So you're going to have to draw this in LT Spice, but I'll just draw it here to start with. Right, we've got a 15 volt source and we have 2 resistors, and the output we want across one of the resistors, let's just make that one the ground. The output we want from one of the resistors is 3.5 volts. And if that one's R1 and that one's R2, we know that that equals R2 divided by R1 plus R2 times 15. And then the trick is to choose one of the resistors randomly, R2 maybe, and that'll then give you an equation that you can solve to figure out what the other resistor is. So if R2 is 1000, that'll just leave R1 as the unknown, and you can solve the equation that way. And right, so the aim is for you to do all the calculations first, build the circuit, measure the circuit in LT Spice to make sure that your calculations match what LT Spice is telling you, and do all of that. So there should be 2 LT Spice circuits, one with the 5 resistors that I just did, and one like this, so that you can validate your design of the voltage divider. Any questions about anything there? Just remember, try and just submit a single file. You should be able to take screenshots of your LT Spice assignment, LT Spice circuits, and insert them into the spreadsheet. You can use the spreadsheet to do your calculations if that makes sense. And I think it's reasonably well set up to report out on these experiments. Anybody got any questions about Lab 3? Okay. Just a reminder, let's just actually quickly look at the assessment calendar, assignment calendar. Right, so Lab 3 is due next week at 11:59 p.m, as is the mesh analysis homework 4. You should have enough background now to tackle homework 4. In web work, you can take as many tries as you like. I suggest, if you get frustrated with it, take a break and go back. If you still can't figure it out, take a screenshot of what you're doing in web work and send it to me either via email or via Discord messaging. And as I think I said, my availability varies greatly, so sometimes I'll get back quickly, sometimes it might take a day to get back to you, depending on what my usual teaching load is. And then I just thought it would be good, right? So after that, there's another lab, this time on a current divider and Kirchhoff's current law. And then there's a nodal analysis homework. Right, that takes us to there. Then there's a lab 5 on mesh and nodal analysis. Then there's a homework on Thevenin and Norton. Then there's a lab 6 on superposition and a homework on superposition. And then there's a lab on Thevenin and Norton. And then I give a bit of a break, because by the time we get to there, that is there being April, the beginning of April, we're going to shift gears a bit, and we're going to do everything we did before, what we're doing now, except we're going to be doing it using complex numbers. And we're going to be including resistors, capacitors and inductors in our circuits rather than just resistors like we're doing now. Once we get that under our belts, then there's the lab for phasors, and the homework for phasors, and the lab for transients and the homework for transients. Just looking at the way I've got that organized now, I may reorganize that so that the homework for phasors is done before the lab, but we'll see how we go. And by that stage, that is about the end of semester. That's May, first couple of weeks of May. So that's the work ahead for the semester. Any questions? Okay, so I've talked about the lab. So thank you for reminding me about that. I'll have to make sure that I add that for lab 4 for next week, so that we can talk about the current divider lab as well next week. So let's tackle a new subject, nodal analysis. And remember, a node is an area of constant voltage, right? So, and as I said in the intro to this session, whereas mesh analysis applies KVL, nodal analysis applies KCL, Kirchhoff's current law, instead of the voltage law. So that's the one we're doing there. And right, here's the circuit that we started mesh analysis with, right? And remember, the answer for VA is minus 14 volts. So nodal analysis is a bit different. It uses nodes, and the idea is that we figure out first of all which are the nodes, right? Remember, in mesh analysis, the first thing we do is define the mesh currents. In nodal analysis, the first thing we do is define the node voltages, right? So or identify the nodes, right? So here we've got this, because this is called VA, I'm going to call that node A, and I'm going to call that node B, and I'm going to call that node C. Okay, so that's the first thing to do. And then we go through and look at each element, each resistor, and define its current in terms of the node voltages. I'm just going to check what's down here. Okay, so that it does have the picture. Right, so that's the next step. Then we, at each node, we apply Kirchhoff's current law. We don't use the reference node, we don't use the ground. Then we distribute in group-like terms, and then we profit. We solve the system. Okay, so let's see what that means for our simple circuit, our example. Right, we identified the nodes, and as I said earlier, a node is an area of constant voltage, but they're usually drawn as dots. So just because there's a blue dot here, that doesn't mean that's the only part of the node. The node actually encompasses all the area of constant voltage. Right, so that's A, just to make it stand out now that I've drawn over the VA. Okay, so that was step one. We've done step one. We've identified the nodes. Now we need to express the element currents as functions of the node voltages. Okay, so the element currents, the elements are the resistors, right? So IR1. Now, what we haven't done is defined the direction of the currents. So I'm going to go through and define the direction of the currents now. Okay, so this is IR1, and sometimes it helps to label everything, even though it's clear from the subscript which item it is. It sometimes helps to label them. Okay, so IR1 is flowing in that direction, and that means this is the assumed to be the high point. So IR1 is, let's try that again, VB minus VA on R1, R2, IR2 is just equal to VA, right? It's actually VA minus 0 because there's the ground, but for simplicity we just write it as VA on R2. Then R3, now we're going this way for R3, so it's IR3 equals VC minus VA on R3. And then lastly we've got R4, IR4, and it's very similar to IR2, it's just VC minus 0, but just to make things a bit simpler, it's VC on R4. Okay, so that's writing out the element currents. So we've identified the nodes, we've expressed the element currents as functions of the node voltages. Now we apply KCl at each of the nodes except for the reference node. Right, so KCl at B right, we actually don't have a KCl at B, right? And just like in mesh analysis, when there's a current source, a single current source, a current source with a single mesh current flowing through it, it's a freebie. And in nodal analysis, there's an analogous freebie, and the analogous freebie is that when there is a voltage source connected between the reference node and a node, then we can write out the node voltage directly. Okay, so in this case, we can just write out that the voltage at B is equal to minus Vs, right, which is minus 21 volts. It's a freebie. There's an analogous supernode issue, which I'll talk about later, where if the voltage source is connected between two other nodes, or two nodes other than the reference node, then you've got a similar problem. You can't write a Kcl equation for the nodes on either side of that voltage source. So you have to use a supernode, and I'll explain that later. Let's just get through the introduction to nodal analysis. I'll talk about supernodes next week. Okay, so that's Kcl at B. Let's do Kcl at A, right? And we've got IR1 flowing in, IR3 flowing in, and we've got IR2 flowing out, right? It's going in the opposite direction, so it's negative. And then we can fill those numbers in, right? So IR1 is VB minus VA on R1, which is 6. R3 is VC minus VA on R3, which is 14. And then minus IR2 is VA on R2, and R2 is 24. Okay, and then the Kcl at C, we've got minus IR3 minus IR4, because they're both flowing out, equals 0. So IR3 is, so that's, I'm going to negate it, so I'm just going to swap the order of VA and VC. So it's VA minus VC on R3, which is 14, minus IR4, which is minus VC on R4, which is 10. That equals 0. Okay, so now in this approach, in nodal analysis, the unknowns are the node voltages, VA, VB, and VC. We already know what VB is, right? So what we could do, right, we know that it's minus 21, so we could replace it here, right? And so now we've just left with VA and VC as unknowns. Excuse me. I'm going to reorganize this so that it maybe looks a little better, so it's just in terms of VA and VC. So what we've got is we've got minus 1/6 minus 1/14 minus 1/24 VA plus 1/14 VC, and that equals 21 on 6, right? Because we've got negative 21 on 6 over here. So there's one equation, and then this equation coming down here gives us 1/14 VA, and then depending on how you want to write it, but I'm going to write plus minus 1/14 minus 1/10 VC equals 0. And then I can write down our matrix formulation, right? So it's going to be minus 1/6 minus 1/14 minus 1/24 1/14 and 21 on 6, and then this one is going to be 1/14 minus 1 on 14 minus 1 on 10, 0. So there's our RF matrix, and let me just pull up MATLAB again, and I'm just going to use parentheses just to make sure I get the right groupings. Okay, and that's telling me that VA is minus 14, which is the answer we were looking for, and that VC is minus 5.833. Right, so that says that, let's get the right colour that we can actually see on the white background. No? There we go. So that says that VA equals minus 14 volts and VC equals minus 5.833. Okay. And that was an earlier MATLAB version that I did. Right, so you can see the results there. And I think I want to so again we can apply the nodal analysis in exactly the same way, right? The first time, and I probably should have reordered my nodes before. I prefer nodes going in alphabetical order, right? And again, I'm drawing dots, but remember it's an area of constant voltage. So there's our A, B, and C. That was our first step, right? Identify the nodes, express element currents as functions of the node voltages. So the problem we have here, right, is if we've got IR1 and IR2, and let's make IR3 go that way and IR4 go that way. The problem we have is that this is a current source. It's not a voltage source. So we can't say, well, we can say VA minus VB on 2 equals IR1. We can say that, but it doesn't help us because we can't figure out what VA is because it's a current source. Current sources don't tell you what their voltages are. But it's pretty easy to see, I hope, that IR1 equals IS. Okay, so that's a no-brainer. Then we can go through the other elements, right? IR2 equals VB on R2. IR3 equals, it's going that way, so it's VC minus VB on R3, which is 4. IR4 is just VC on 2, and we can say that VB is VB on 4, because R2 is 4. Okay, so we already know the currents flowing through here, so we don't have to do KCL at node A, but KCL at B. We have IR1 plus IR3 minus IR2 equals 0, and we can write that down as so IR1 is IS, so it's 6, plus IR3, which is VC minus VB on 4, minus IR2, which is minus VB on 4. That equals 0. And then the KCL at C, we've got IR3 minus IR4. Sorry, minus IR3, right? Because IR3 is flowing out of node C and IR4 is flowing out, so they're both negated, and that equals 0. And then we can write that down as minus IR3. I'm just going to swap VB minus VC to negate it on 4, and then minus VC on 2 equals 0. And then let's just grab the white pen over here so we can write out our equation. So for this one, there's going to be a minus 1/4 minus 1/4 times VB. There's going to be a quarter VC, and there's going to be a minus 6 on the other side. And then for this one, there's a 1/4 VB and a minus 1/4 minus a half VC, and then there's a 0. Okay, and we can plug some numbers into that. So minus 1/4 minus a quarter, not minus a 14th. Okay, so our VB is 14.4 volts, and VC is equal to 4.8 volts. So, does anybody have any guess what's going to happen with this circuit? Well, it's right. You've only got current sources, right? So IR1 is just going to be equal to IS1, and IR3 is just going to be equal to IS2, provided you define them in the directions that I've just drawn. Okay, there's nowhere else for the current to go. The only, so this is A, B, and C. The only sort of unknown one is that IR2 equals VB on 2000. Okay, and then we can we can look at the equations, right? The only real one that is the only Kcl equation we have, non-trivial one, is the Kcl at B, right? And that says that IR1 minus IR2 minus IR3, because IR2 and IR3 are flowing out of node B, is equal to 0. Okay, so IR1 we know is 2 milliamps. IR2 we know is, well, I'm going to write it like that. IR2 is VB on 2000, and then IR3 is 6 milliamps, and that equals 0. Okay, and if we take that across there, we get minus VB on 2000 equals, that's going to be left over with 4 milliamps, 0.006 minus 0.002, so that our VB is equal to minus 2000 times 0.004. And my MATLAB is locked up again for some reason. Wonder why it does that. So let's just minus 2000 times 0.004, right? It's minus 8 volts. Sort of makes sense if I'd actually thought about it. Now, how do we get VA and VC? Well, we know that VB is minus 8 volts. Right? We just calculated that. And now what we've got to do is see where do we go from there. Well, if we go from VA to VB, we're going up in voltage, right? That's a voltage drop across the resistor. So VA is equal to VB plus IR1 times R1. And VC, that's a voltage drop. So VC equals VB minus IR3 R3. Okay. And I'm going to leave the rest until next week to go through as an example. But I thought I'd just quickly show you what I talked about as identifying a supernode, right? Remember, it's if you've got a voltage source connected between the reference node and another node, then it's a freebie. You immediately know what the voltage is. When you've got a case like this, it's a problem because it's a voltage source. Until we've analyzed the circuit, we don't know what the current coming into or out of it is. So just like with a super mesh, we do something a bit different, and instead of getting two for the nodes on either side of the of this voltage source, instead of getting two Kcl equations, we get one Kcl equation and one Kvl equation. Right? Let's just quickly. I won't solve this. I'll go through it in more detail next week. Right? But the Kvl equation we get from this is that VC minus VB equals 8 volts. And the equivalent idea to a super mesh in nodal analysis is a super node. And what we do is we just draw a box around the two nodes that are on either side of the voltage source and say, forget that what's inside the box. Kirchhoff's current law still has to hold, right? So we know if there's a current flowing, if we've got current flows like that, then we know the Kirchhoff's current law equation we get is IR2 minus IR3 minus IR4 minus IR5 equals 0. But I'll go through that in more detail next week and we'll solve this one. And then we can make things more complicated and have dependent sources just like we did in the mesh analysis one. Okay? So that's all I've got for this week. I'll cut it a little bit earlier. I think we all deserve a break now and the rest of the weekend. Does anybody have any questions about anything that I've gone through today? Right, so I might just have a quick look at the tutorial questions on nodal analysis. We'll do those next week. I think, so what I'd suggest you do, right, here's our mesh analysis questions. Let's just have a quick look at the nodal analysis questions, right? There's one with a current source and a voltage source. And there's one, again, with a similar idea. I don't know whether there's much difference between those two. Just the values that are there, I think, are different. There's a more complicated one. We've got a current source and two voltage sources. VS1 is upside down, so it's negated. And there's another similar one, but just with different numbers. Okay, but we'll do those next week, and I'll do the usual thing of splitting us up into. But I suggest you have a go at the tutorial questions before next week if you've got time, and we'll tackle them then. Does anybody have any questions? Do you want me to finish with? Okay, if not, let's leave it there, and I will talk to you next week. Thank you very much for your attention.
Thank you, Professor.
You're welcome. Have a good weekend, everyone.
Yeah, have a good weekend.
See you next week.
Yep, bye-bye.
Thank you, Professor. See you next week.
Yeah, see you next week.